There's a quiet revolution happening right on top of our houses. It's not just about the solar panels you see, but about the hidden smarts that actually make them work. Today, we're going to pull back the curtain on the real hero of solar power, the inverter. And specifically, we're diving deep into the tiny computer chip that acts as its brain, the part that makes every single sunbeam count.
So, to really get why this matters, you gotta look at the big picture. This isn't just some passing trend. We're talking about a massive, global shift. Just look at this chart. Renewable energy, and especially that bright yellow slice for solar, is on an absolutely explosive growth path. We are fundamentally changing the way we power our entire world.
And this is no small change. The folks behind our source material, they call it nothing less than a fourth industrial revolution. Yeah, that's the scale we're talking about here. And sitting right at the heart of this whole revolution is the technology that makes solar power practical, efficient, and, well, smart.
So what's the big problem? What's the one hurdle that every single solar panel system has to overcome before it can power your TV or your toaster? It all boils down to a fundamental mismatch, like trying to fit a square peg in a round hole when it comes to electricity.
Okay, so here's the challenge in a nutshell. Your solar panels, they're out there soaking up the sun, and they produce what's called direct current, or DC. Think of it as a steady one-way street for power, kind of like a battery. But your home, all your appliances, and the entire electrical grid, they all speak a completely different language, alternating current, or AC, where the power rapidly zips back and forth. The job of being the universal translator between these two falls squarely on the solar inverter.
For a long time, the solution was just one big, clunky, central inverter for a whole string of panels. But technology never stands still, right? It got smaller, it got smarter, and it got a whole lot more effective. And this evolution led to a huge breakthrough, the microinverter.
So instead of one giant box trying to translate for everybody at once, the whole idea behind a microinverter is it's simple, but it's totally revolutionary. You give each and every solar panel its own small, dedicated inverter. It's literally like giving every single panel its own personal brain.
And why is that such a big deal? Well, the results are just staggering. By giving each panel its own brain, you increase the total amount of energy you get by 5 to 25%. That is a massive gain in efficiency. So the question is, where does all that extra power come from?
So how is that even possible? Well, the biggest factor is something called partial shading. In an old system, all the panels are wired up in a long line, kind of like old-school Christmas lights. If just one of those panels gets a little shadow on it from a tree branch, the output of the entire string of panels just plummets. But with a microinverter on each one, only that single shaded panel slows down. The rest just keep cranking out power at their full potential. It also solves things like panel mismatch, where tiny differences between panels mean one weaker one can drag the whole group down. Basically, each panel gets to be the best it can be. Okay, now we're going to zoom in and get a little technical. To really see how this works, let's think of the microinverter as having two main parts, a body and a brain. First up, let's look at the body, the actual physical hardware that's doing all the heavy lifting.
All right, this diagram is our map. Now, I know it looks a bit complex, but this is basically the physical anatomy of the inverter's body. All these components, the main circuit, the drivers, the transformers, this is the hardware that's responsible for taking in one kind of electricity and physically turning it into another. So all those parts we just saw, they're the muscle. Things like MOSFETs and drivers, they're the real workhorses here. They take that raw DC power coming straight from the panel, and by switching on and off incredibly fast, they physically chop it up and reshape it into the smooth AC power that can be fed into the grid. But muscle without a brain is pretty useless.
And that brings us to the most critical component of all, the part that tells all that muscle exactly what to do, when to do it, and how to do it absolutely perfectly. This is the brain of the whole operation.
So, let's go back to our map. You see this highlighted section right here? That's the controller circuit. That's the brain. Specifically, it's a super powerful C2000 microcontroller from Texas Instruments. This one little chip is running the entire show, constantly watching the panel, watching the grid, and making thousands of pinpoint calculations every single second to manage the power conversion. So, what's one of this brain's most important jobs? Well, it uses this really clever technique called a phase-locked loop, or PLL. I want you to think of the electrical grid as having a very specific heartbeat, pulsing away 60 times every second.
Before the inverter can inject a single watt of power, its brain has to use the PLL to listen to that heartbeat and perfectly synchronize its own rhythm to it. It has to match the grid's frequency and phase flawlessly. And this really shows you the sheer processing power we're talking about. This microcontroller is constantly solving complex math equations, making tiny adjustments in microseconds, all to make sure the AC power it's creating is a perfect, clean sine wave. Any little impurity or mismatch could mess with the grid, so perfection is literally the only option.
Okay, let's zoom back out. We've seen the muscle, we've seen the brain. Now, what does all this incredible microscopic engineering actually mean for the real world? What does all this intelligence actually let us do?
This brain is what makes solar power not just possible, but actually reliable and safe. It handles soft starts to avoid power surges. It's always hunting for that maximum power point for every panel, but probably its most critical job is safety, specifically something called anti-islanding. Now think about this. If there's a power outage, utility workers have to go out and fix the lines. The last thing they need is your solar panel still pumping electricity back into those lines, creating a dangerous island of live power. The old way of preventing this used slow, clunky mechanical relays and contactors. But the C2000 microcontroller, it's a whole different game. It intelligently and instantly senses the grid is down and shuts the inverter off. No moving parts, no delay, just smart, fast, and reliable safety, all managed by this tiny chip.
So when you put it all together, you realize the tech inside a microinverter isn't just about a simple DC to AC conversion. It's about intelligence, it's about optimization, and it's about safety. It's about wringing every single possible watt of energy out of every single sunbeam, and doing it safely and efficiently.
And all this leaves us with a really fascinating question for the future. We now have millions of these little computers sitting on rooftops all over the world, each one optimizing a single solar panel. As our entire grid gets smarter, how are we going to harness this incredible distributed intelligence next? What new possibilities will that unlock?